Alright, we're talking here about ideal solutions. I just quick review when we showed for the ideal solution. This is the entropy of mixing of an ideal solution. Don't know if I showed this one or not. This was just to see the what it actually looks like. This is the ideal entropy of mixing in joules per mole minus Rxa log Xa plus Xb log Xb. To give you an idea of the order of magnitude, of course, it's the maximum here is about 5.78 joules per mole Kelvin, and of course the ideal entropy is always positive and symmetrical and independent of the temperature. So that's what your ideal entropy curve looks like. So when you're looking at excess entropies, which are the deviation from this, you get an idea. I mean, an excess entropy of 1 joule per mole is not very big. An excess entropy of 5.5 joules per mole is an ideal, has an excess entropy that's equal to the ideal entropy. So to give you an idea of the order of how far away you are from the ideal solution. That's what I wanted to do. Oh, come on. Wow. That's not it. Oh, the whole thing's gone. These stupid cryptic symbols. Okay, so that's your ideal entropy of mixing. And I talked yesterday about the partial properties, so your delta S of mixing is Xa times the delta S partial of A plus Xb times the delta S partial of B. So the delta S, the partial entropy of an ideal solution, the partial entropy of component A in an ideal solution is minus R log Xa, and the partial entropy of component B is minus R log Xb. For an ideal solution, all the partial heats and the integral heats are 0 for an ideal solution. Since the partial Gibbs energy is defined as RT log activity of A, delta G of an ideal solution is delta H minus T delta S is RT log of X of A. Delta G is RT log activity of A, so the activity of A is Xa for an ideal solution. Okay, so we talked about that. I can actually get to that now. And then we talked in general about partial properties. Oh, Lord. All right. So again, if you have just to review, you have this is the called the integral reaction of forming a solution. So this is delta, the change in energy for mixing pure A and pure B to form a molar solution is the integral molar Gibbs energy of mixing, which would be recognized here. These goes from the curve then of the Gibbs of the volume goes from the volume of the pure A V0A to the volume of pure B. The tangent construction shows that the partial property is given by taking a tangent at this point, extending it to the two axes. So this is the partial molar volume of A and partial molar volume of B at that temperature, and this distance here is called delta VB, which is the partial molar volume of mixing of component B, which is defined as VB minus V naught B, and so on, and then all these equations apply. And or if you plot delta V, you get the thing this way around, and delta G is generally plotted like that, and this is the one we're most interested in. Okay, so delta G, this is delta, come on. If the damn thing disappears. All right, so this is the integral Gibbs energy of mixing. So the integral Gibbs energy of mixing, delta G or delta GM is the same thing as the Gibbs energy of this reaction. If the solution is stable, this will always be negative. delta G. This distance here is delta GA, which is the partial Gibbs energy of mixing of component A at that point, which is GA at that point minus G naught A at that point, or delta GI partial is the same as mu I. So this is delta mu I is mu I minus mu naught I is RT log activity of I, where the activity of I is the value at that point. So we can say that delta G is delta GA plus XA plus delta GB times XB, and this is a very general equation which applies for all solutions. That's just the definition of the activity. Okay, clearly if the solution is stable, delta G will be negative, delta GA will be negative, mu I minus mu I naught will be negative, and the activity will be less than 1. So the activity is always less than 1 in an ideal solution. It's equal to 1 for the pure material. Always less than 1 in a stable solution, equal to 1 for the pure material. And the activity, the ideal activity is equal to the mole fraction, so the ideal activity is equal to XA. You can see then that this curve has an infinite slope here, so that as you go to pure A, delta GB, the intercept here goes down to minus infinity, and the activity of B in pure A is equal to 0. Just a review of what I said, if you plot the delta G as RT log activity of A, which is the tangent intercept, you're going to get curves that look like this. So I presume you've all looked at this and thought about it. This one I think was the last place I was yesterday, okay. So finally, delta GI or delta mu I is defined as mu I minus mu naught I. This is a definition of activity, and this applies generally. For an ideal solution, the ideal activity is Xi, so the ideal Gibbs energy, partial Gibbs energy of mixing, or the ideal delta mu I, or the ideal, or the relative mu I, there's all sorts of names for it, is equal to RT log X. Okay, we can write activity as activity coefficient times X. For an ideal solution, the activity coefficient is 1, and so clearly in an ideal solution, the activity is equal to the mole fraction. All right. I presume you've all looked at that, and there's been problems. Now I want to show a couple of things, so let's go to the chapter here. Alright, and as well, I'll put on the figures. Okay, and let's go to section 4.1. This is just going to give you an idea now of the okay, this is actually drawn to scale. This is the Gibbs energy of the actual Gibbs energy of gold copper mixtures. Liquid gold, this is liquid gold and copper. I'm reading section 4.1.1 now. So this is the Gibbs energy of 1 mole of liquid solution as a function of composition at constant temperature of 1100 degrees, expressed as the mole fraction of copper in the liquid solution. Okay, the curve varies between this point here, which is the chemical potential of pure gold, or G naught of pure gold. This is an arbitrary point that I put here because there's no absolute zero for it, and this is the chemical potential, or the Gibbs energy, partial Gibbs energy of pure copper. And these 2 points here are the chemical potentials of gold and copper in the liquid at that composition. And this distance here then is RT log activity of copper, or delta mu copper, and this is RT log activity of gold, or RT log delta mu gold at that point. And just to show you, this is actually drawn more or less to scale, so that's what an ideal solution more or less looks like. I'm going to go to section 4.1 here, which is on page 34. Okay, this illustrates the tangent construction. The tangent construction is that the tangent construction, the two lines equal. Another way of expressing the tangent construction is in equation 92. And you might want to try to prove that yourself, because it gives you a chance to think about it. And here you have a system A, B, and here you have your tangent construction. This point here then gives you G. This gives you G at this point here. This gives you mu A, this gives you mu B, and this value here is G, Gibbs energy at that particular point. And we can show that chemical potential of I is G plus 1 minus Xi dG dXi. Okay, so this is Xi here, XB. Okay. And so what we're saying is that at this point here, we're saying the chemical potential of B at this point, in other words, if you draw the tangent, it would be this point. Chemical potential of B at that point is equal to the Gibbs energy at that point G, plus, and this value here then is XB, plus 1 minus XB, in other words this distance here, times dG dXB, which is the slope of this line. Okay, it's because it's a tangent. Okay, so I think that's obvious that the chemical potential here is equal to here, plus, you draw this over here, this distance here. The chemical potential is equal to G plus this distance, and this distance here is at 1 minus XB times this one. Okay, so that's another way of looking at it. Now you have to be careful. Okay, so that's this equation, which is quite useful. Notice that this equation is in terms of the molar Gibbs energy. This is the molar Gibbs energy per mole. Okay, because that's what I've drawn there, the molar Gibbs energy. So it's dG dXi. Okay, but you can make a mistake. The other way of looking at chemical, so that's one way of calculating chemical potential in terms of the molar Gibbs energy and the molar Gibbs energy G, small g, and the chemical potential in general. However, the chemical potential of B is equal to dG dNB at constant Na, T, and P, where this is the extensive, the total, not G molar, but the total G. Okay, which then is equal to D Na plus Nb G dNb. We'll be doing this later, you'll see what I mean. This people often make a mistake. They say mu, the definition of the chemical potential is dG dNb, the number of moles of B, but this is the total. So if you put in an expression for the partial, you got to multiply it by the total number of moles if you want to make it work. This is a practical thing when you're doing some of your derivations, but we'll be doing a lot of that later. Okay, so we talked about the chemical potential. Same thing was it before, relative chemical potential. The isothermal Gibbs energy of mixing. The delta G integral can be divided into heat and an entropy term, so that's your heat of mixing, minus T times your entropy of mixing. And similarly, the partial property, the delta mu of I, or delta G of I, is the same thing. Delta mu of I, remember, is the same thing as the delta G partial of I, so it's delta HI minus T delta SI. In general, delta G, anything is equal to delta H for the same thing minus T delta S for the same thing. So if this is a integral Gibbs energy, then these are the integral heats and entropy. So this is a partial Gibbs energy, or delta mu I, this is delta HI minus T delta SI, and so on. You can write GI as HI minus SI, delta G of fusion is equal to delta H fusion, and so on. And similarly, the partial heat of the heat of mixing, the integral can be divided into the weighted sum of the partial heats, the entropy, the same thing, and so on. So we define the activity of a component is defined as RT log activity of I, and I'm going to draw something now that's not in here. You've often seen, I'm sure, the activity, you have the activity of a component is defined as the partial pressure of the component divided by the partial in solution divided by the partial pressure of the pure component. Okay, this is the vapor pressure. Activity of I in a solution is equal to this is the vapor pressure of I over the solution divided by the vapor pressure of I over the pure material at the same composition. So in other words, if I have a solution here, I have a liquid solution of A and B, or a solid solution. So here I have a solution. I have a solution of A and B, liquid or solid, let's say, and up here I have a gas. And the gas, the partial pressure of A is PA at equilibrium. So that's the gas pressure at equilibrium, so that's the vapor pressure. So that's the equilibrium vapor pressure over the solution. I now imagine I have over here pure A, and up here I have a gas, and that's at equilibrium with the gas, and that P naught A is the vapor pressure of A over. Sorry for the notation, this is not standard state pressure, this is vapor pressure. I just put the zero. The zero doesn't mean standard state, the zero means vapor pressure of pure A. Anyway, that's the part, that's the vapor, it's the equilibrium vapor pressure over pure A. This is equilibrium vapor pressure over the solution. And the activity of A in the solution is equal to the vapor pressure of A over the solution divided by the vapor pressure of A over the pure material at the same temperature. Now sometimes you'll see this in books as a definition of activity. This is in no way the definition of activity. The definition of activity is delta mu A equals RT log activity of A. That is your definition of A. Of activity is defined in terms of the chemical potentials, not vice versa, but we can derive this. Try to understand it. First of all, it's interesting, of course, if you have pure A, then PA is equal to P naught A, so the activity is 1. If you have a solution, which is a stable solution, PA will be less than P naught A. Okay, it's going to be, you put it into the solution, it lowers the vapor pressure. Why would that be the case? Well, let's suppose it wasn't the case. Let's suppose that you put a tube in between here, and you allow the gas phases to communicate with each other. If PA were greater than PA0, what would happen is A would leave here, move over here, and condense on here, and the solution would spontaneously separate. Okay, so spontaneously separate would mean it's not a stable solution. What actually happens if it's a stable solution, if you did this, A would evaporate here, go over here, and deposit here, and eventually A would go into solution because that's your spontaneous reaction. Okay, so P must be less than P naught. This can't be a definition. I mean, suppose a solution is an iron-carbon solution at room temperature. I mean, the partial pressures are 10 to the minus 50th atmospheres. I mean, you can't really define something in terms of a gas phase that doesn't even exist. Okay, so similarly, what if the gas phase is not A, but it's divalent, it's A2? Then this doesn't work either. Let's do a little, just derive that, because I think it's worthwhile, because it gives an idea of the, let's say you have zinc. Here I have zinc liquid producing zinc gas, and let's say that's pure. And let's say this is zinc gas at P naught, zinc. So here I've got zinc liquid in equilibrium with the zinc at its vapor pressure. Okay, so delta G for this reaction is 0. Liquid, this is pure liquid, and I fix the partial pressure. I fix the pressure of zinc, so it's equal to its vapor pressure at that temperature. So that's 0. Now I consider here zinc liquid in a solution. So this is zinc dissolved in something, dissolved in lead at a certain composition, mole fraction of zinc. And this goes to form zinc gas at P zinc, which is the partial pressure of zinc in equilibrium with the solution, just like I showed in the, as I showed in the diagram. Okay, and once again, this here, delta G is equal to 0 for that reaction too, because this is the partial pressure of zinc. This is the partial pressure of zinc over this solution. Everybody clear on that? Okay, so now I want to do a cycle. I want to get from here. I want to get from here to here. So what I do is I would take, let's go this way. Here I would have delta G equals something, and here delta G equals something. So this plus 0 plus this equals 0. Okay, going around this way. Same thing. Okay, I'm going around the circle. Getting from here to here, delta G is 0. So I decide to go this way. I go here, then I go here, then I go here. Okay, so this is delta G is 0 too. So I take the pure liquid zinc, I put it into a solution, and what's delta G for that reaction? That delta G is mu of zinc minus mu naught zinc. Okay, or in other words, RT log activity of zinc. It's the Gibbs energy for putting the zinc in solution. You have to think of this, okay, if you want to look at it as a mole, this is an infinite amount of solution. You're not changing the composition of the solution as you put a mole of zinc in it. Or we can just assume that you have dn moles of zinc.
So if you really want to do it mathematically, the delta G for this is RT log activity times dN. Do your mathematics. You're taking 1 mole of zinc pure, you're putting it into an already prepared solution. Okay? And you're not changing the composition of the solution. Okay, so you can either think of it as 1 mole of zinc going into an infinite amount of solution already mixed, so you don't. Okay, you're not creating the solution. You're not taking liquid zinc and mixing it with lead. You're taking a zinc-lead solution already at a constant composition, and you're adding dN zinc moles of zinc to it. The Gibbs energy change would be RT log activity of zinc times dN zinc. Okay, by the definition of activity. Delta G here, you're taking gas at pressure P, and you're changing its pressure to P0. So the delta G there we've already done is RT log P over P0. Or minus RT log P over P0, just compressing, assuming the zinc's an ideal gas. Now if we compare them, we compare this plus this has to equal to 0. So this delta G minus this delta plus this delta G equals 0. So in other words, the activity of zinc is P over P0. So the activity of zinc is that P partial pressure of zinc
Why is del G equal to 0 for second?
Because they're in equilibrium. It's an equilibrium. Here you have pure liquid zinc in equilibrium with zinc gas at the vapor pressure of pure zinc. Here you have zinc in the solution in equilibrium with the gas where the vapor pressure is the partial pressure over the solution.
But there should be some activity also.
No, it's an equilibrium, so there's delta G 0. Two things are in equilibrium, there's no Gibbs energy change. Because that is the vapor pressure. So that's what I showed you. This is this P0, well, that's what I showed you. We have pure zinc here, zinc pure, and the partial pressure above it is P0. Over here you have zinc lead solution, the partial pressure is P zinc. P zinc vapor pressures, the ratio of the vapor pressures is equal to the activities. Okay, so clearly then, if there's no zinc in the solution, if you have a solution of pure lead with no zinc in it, the partial pressure of zinc will be 0 and the activity will be 0. Okay. Activity must be less than 1 or else the solution will spontaneously separate via the gas phase. The activity of zinc and pure zinc is equal to 1, and so on. And then we see this is derived from the definition. This is not the definition, this is derived from this, which is the true definition of the chemical of the activity is the difference in the chemical exponent differential difference in the chemical potentials. Okay, so now this is what you see. Supposing that zinc gas is monatomic. Okay, but now there are many gases which are not monatomic. Suppose zinc gas were diatomic. Just suppose it were. This would be zinc 2, and you'd have 1/2 zinc 2 here. Over here I would have 1/2 of zinc 2 gas. This here then would be the pressure of zinc 2 over the pressure of zinc 2 to the 1/2, or 1/2 RT log P, you got 1/2 mole. So the activity would then be the ratio of the partial pressures of zinc 2 to the 1/2. So if it was triatomic, one zinc 3, it would be P zinc over to the 1/3, and so on. Right? Let us suppose that we have a solution with something in it like sulfur. So here we have a solution of A, B, and it also contains sulfur. So here you got some sort of a solution containing sulfur. Above the sulfur you have the gas phase. Above the solution you have a gas phase, and when it's at equilibrium there will be many species. There will be S, S2, S3, S4. So you'll have a partial pressure of S, you'll have a partial pressure of S2, you'll have a partial pressure of S3, and so on, and these are all up 4, 5, 6, and 8 are all quite large partial pressures. They're all significant. And the whole system's at equilibrium. Okay, so you'll have a P vapor pressure of sulfur. The total vapor pressure of sulfur will be equal to PS plus PS2 plus PS3 and so on. At equilibrium, this is the total partial pressure of all sulfur-containing species over the solution. Okay? But the activity of sulfur is not equal to the ratio of the actual vapor pressures. It's equal to PS over P naught S, where P naught, this is ABS. Over here now we have pure sulfur. And then we would have P naught S, P naught S2, P naught S3, and so on are the partial equilibrium partial pressures, the vapor pressures of each individual species over the pure sulfur. And so the activity of sulfur would be the ratio of the vapor pressures of the monatomic species, which is equal to the vapor pressures of the diatomic species ratio to the 1/2, which is equal to the ratio of the triatomic species to the 1/3, which is equal to, and so on. Okay, so you can't, and this is not equal to the total, this is the ratio of the total vapor pressures. Okay, so the activity, if you're going to calculate the activity as a ratio of partial pressures, it has to be done with respect to the actual species, not the overall thing. Okay, that's why if you're going to one way of measuring activities is to measure vapor pressures by various techniques, such as mass spectrometry and so on, but you have to know what the gaseous species are. If you measure the total vapor pressure over sulfur, over this thing here, you're not going to, if you just take your solution here and your pure sulfur and you measure the total vapor pressure over each, that doesn't give you the activity. You have to know the speciation. Okay. If you know the speciation, you're fine. If you don't know the speciation, you're going to have to measure it, or you can't calculate activities that way. Okay, you know how a mass spectrometer works? We'll talk about that. Mass spectrometer, at the same time, you measure the partial pressures and you measure the species as well. So mass, that's why the mass spectrometer gives you a good way of measuring the activities. You could have it even other problems that you get if you're trying to measure activities by measuring vapor pressures is what if you have species such as AS, or you have species such as here is PA2S. Now you're in real trouble because some of the sulfur is in these molecules mixed up with this other stuff. Okay, so now things aren't going to work at all unless you really know everything that's going on up there. Okay, so that's sort of what activity is. Let's try to explain it to your grandmother. Here we have my ideals. Okay, here we have your AB solution, and up here you have a partial pressure of A above the in the gas phase in equilibrium. So that's your vapor pressure of A over the solution, and over here you have pure A. And over here you have P0A gas, and the activity of A is equal to PA over P0A. And the ideal activity of A, we just went through the ideal solution, is equal to XA. Okay, an ideal solution is one in which A and B are very similar chemically, blah, 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 blah. Okay, so try to explain then why then. Okay, so that's your partial, that's your activity, that's according to the definition. Why should an ideal solution, why should the activity be equal to the mole fraction? Presume your grandmother says, explain it to me. How would you explain it? You can't, you know, I want you to use Boltzmann's equation or reference to entropy and order of the universe. Just why? Why would it be that? Why mole fraction of all things? Okay, what determines the vapor pressure? It's kind of a dynamic equilibrium. On the surface here you got A molecules, little molecules of A sitting on the surface, and then up here you have A molecules in the gas, and at any given period of time some of these A molecules bounce off the surface and go up into the gas, and some of the A molecules in the gas settle down and condense on the surface, and when those two rates are equal, that sets up the partial pressure. Okay? It's kind of a dynamic process. It's not static. You got A molecules going this way and you got A molecules coming down. The two rates are equal. You've got an equilibrium now. Dynamic equilibrium, and that fixes the vapor pressure. As you increase the temperature, the molecules in the liquid are bouncing around more, so they have a greater tendency to fly off, so the rate going into the gas, the rate of evaporation gets greater. The rate of condensation pretty much depends on the partial pressure. which is the density. Okay, the rate of condensation pretty well is a function of P0, if you, as P. If you have twice P, you have twice the density, so there's twice as much chance of a molecule landing on the surface. But the PA, the rate that they're going up depends on the temperature. It also depends on the bond energy. If the bond energy here between two A's is very strong, then that tends to give you a lower vapor pressure, because it holds the thing in solution. If the bonds are weak, the things go off. All right, now let's suppose over here we have A and B on this. Here we have a solution, so on the surface we have A and B, molecules are sitting on the surface. So it's an ideal solution. So it's an ideal solution, delta H is 0. That means the bonds, AB bonds and AA bonds and BB bonds are about the same energy. Okay, so the fact that here the A is pure and here the A is mixed with B, it doesn't change the bond energy. Over here an A is surrounded by A's with AA bonds. Over here it's surrounded partially by B's with AB bonds, but the AB bonds are the same energy as the AA bonds. So the partial pressure of A here is not different because of the enthalpy effect is not making it different. So it's got to be an entropy effect. Basically, there are fewer atoms on the surface. If 1/3 of the surface is covered with A atoms, if the mole fraction of A is, let's say the mole fraction of A is 1/3, then 1/3 of the surface is covered with A atoms. So the rate at which A atoms are going up is equal to 1/3 what it was over here, because there's just only 1/3 as many of them. Okay, the rate at which they go down varies as the partial pressure. Double the partial pressure, you've got. Okay, so the rate at which they're going up is 1/3, so now the rate at which they're coming down when you're at equilibrium also has to be 1/3 of what it is here, so the partial pressure has to be 1/3. So it varies as the mole fraction in a very simple-minded way. Okay, it has to do with simply probability of this. That's way oversimplified, but that would probably satisfy your grandmother. Yeah, but that's why it should be mole fraction, not mole fraction squared, or I mean, half the surface is covered with A, so you got half as many A's per second going up. So in order to have half as many A's coming down, you have to have the partial pressure, have the density in the gas phase. So the number of molecules would hit the surface at any given period of time is 1/2 what it would. All right, so if the bonds are stronger in the, so we have, if the bonds are stronger in the solution, then is that going, that holds the, in the solution than in the pure material, that holds the material into solution. Okay, which is going to make it stronger, so it's going to make the activity less than the ideal activity. Okay, so this depends on delta H. If delta H is less than 0, you have an exothermic heat of mixing. That means the bonds in solution are stronger than in the pure material. That's going to lower the activity. Gives you negative deviations from ideality. If delta H is positive, they're less strongly held, so you'll get positive deviations. The activity will be greater than the ideal solution. So that's your enthalpy effect. So we're going here, the use of activities and calculations of chemical equilibrium conditions is illustrated by the following example. Actually, it was Einstein, I think, who said if you can't explain it to your grandmother, you don't really understand it. Just try sometime if you think you understand something, that you're going to explain it to somebody who doesn't have all the equations and the theory. Sometimes you come to the conclusion that you don't really understand it yourself. Okay, we're using activities in chemical reactions now. So now you have a liquid solution of gold and copper, say with a mole fraction of 0.6. Exposed to an atmosphere with a certain oxygen partial pressure, will Cu2O be formed. So there's your reaction. So your liquid copper and oxygen could be in equilibrium with Cu2O. The copper now is in a solution with gold at 60%. If the reaction proceeds, and we assume the copper oxide is solid. So if the reaction proceeds with forming Dn moles of copper oxide, so we go this way, we form Dn moles of copper oxide, then 2 Dn moles of copper are consumed, and the Gibbs energy of the gold copper solutions changes by this much, 2 times dg dn dn. That, of course, is the chemical potential of copper. So the total Gibbs energy then, as this reaction proceeds to the right, forming Dn moles of copper oxide, the dg is you're forming dg dn, you're forming
dN moles of copper oxide at this chemical potential. You're removing 1/2 moles of oxygen at its chemical potential, and you're removing 2 moles of copper at its chemical potential, which is given here, and we end up with dGdN is delta G of the reaction, which is delta G naught plus RT log PO2 to the 1/2 over activity of copper squared, which basically comes out to exactly the same thing as we did before. You have your equilibrium ratio here, PO2. You simply, if this were a gas, then you would simply have the partial pressure of copper to the -2. If it's a solid or a liquid, you simply replace partial pressure in your equilibrium constant by the activity, and that's why we define activity as mu as RT log activity. Okay, but so this is all nice mathematically. Let's again do that in a little simpler way, just to think about it. Oh, by the way, there is one other thing I forgot to say. When you say the activity is equal to the vapor pressure, this just goes back P0y. I said, first of all, you have to know that the assumption was that the gas was monatomic. If it's not, then you have to take into account your speciation. The other assumption we made was that the gas is ideal, of course. Our delta G for compressing the gas was RT log P. Otherwise, you would have to take into account the non-ideality of the gas here as well. I won't bother going into that right now. In just about every case that you're measuring this, though, it's going to be an ideal gas because you're down or less than 1 atmosphere. I was going to do the same thing here. This is kind of mathematical looking. I like to look at things in terms of cycles. Maybe that's because the way I looked at it. I learned it, I mean. Let's go zinc plus chlorine forms zinc chloride. And here I'll have pure liquid zinc. Here I'll have chlorine at 1 atmosphere. I should be saying bar these days. Make the physicists happy, 1 bar. And zinc chloride pure liquid. And so this is delta G0. Because everything's in a standard state, right? Pure liquid zinc chloride, and chlorine at 1 atmosphere. Now let's suppose I have the reaction zinc in solution with something like zinc lead solution. Okay. So this is zinc in the solution plus chlorine at some pressure PCl2. This is at P naught Cl2 equals 1. Forms ZnCl2 in solution. So for example, PbCl2, ZnCl2 solution. So you have it in the solution. So we can imagine here we have 2 phases. Here we have a zinc lead metal phase. Then here we have a zinc chloride, lead chloride liquid phase. Consider it to be like a slag. And up here we have the gas phase, which consists mainly of chlorine. So you got your 3 phases there. You have zinc that's in solution in the zinc lead. You have chlorine up here that's at the equilibrium partial pressure, PCl2. And over here you have zinc chloride in the solution, in the salt solution. And this is delta G. And so delta G is delta G naught plus this delta G plus this delta G plus this delta G. Okay. Alright, so delta G here is equal to this plus this plus this plus this. Okay, we've already done this. This is changing the chlorine pressure from P to P0. So here your delta G is RT log P over P0 of chlorine. Okay, here you're taking pure zinc liquid and you're putting it into solution. It's the same thing as I did with that other little cycle with the vapor pressure. Again, look at this as a solution, a huge amount of solution that's already prepared at constant composition, and I add 1 mole of zinc chloride without changing the composition, or I just allow Dn zinc chloride moles to go down. And the Gibbs energy change for that then, the Gibbs energy change for this is RT log activity of zinc chloride, mu minus mu naught by definition. Okay, so it's mu minus mu naught of zinc chloride. So taking the pure liquid, putting it into solution, the delta G is RT log activity of zinc chloride in the solution. Definition.
And in here, I'm just going the other way. I'm taking the zinc out of solution, so this is minus our delta G for this reaction. And mine, because I'm going the other way, is minus RT log activity of zinc in that solution. Okay, so now the delta G is equal to delta G naught plus this, plus this, plus this. And so delta G is delta G naught plus RT log activity of zinc chloride divided by the activity of zinc times the pressure of chlorine. Okay, when the solution's at equilibrium, delta G at equilibrium, delta G is 0, so delta G naught is minus RT log of the equilibrium constant being this ratio at equilibrium. So it's exactly the same thing as you do when you have the gases, but now, so you write any chemical reaction, delta G, the delta G is delta G naught plus RT log of the ratio. If it's a gas, you write the partial pressure. If it's a solid or liquid, you write the activity. So that's why we define activity that way, for convenience in this type of equation. Okay. That's essentially the same thing as we're saying here, but maybe looking at it a little bit differently. If you don't like that and you like that, it's fine. Okay, so for a solid or in the equilibrium constant, the activity for a solid or liquid, the activity replaces the partial pressure, which is what you put for the gas. And of course, you still have the stoichiometric factors. If it's 2 copper, then you have activity minus 2. Okay, so that's why it is defined that way. All right, so as you lower the activity of zinc chloride, let's say we lower the activity of zinc chloride, that makes the zinc chloride more stable in the solution than it was before. So as you lower the activity of zinc chloride, this solution becomes more and more stable, and that drives the reaction to the right. Okay, because this now becomes more stable, and you can see that as zinc chloride, the activity of zinc chloride becomes smaller. Delta happens about this time of year. This is the stupidest arrangement. Okay, as the activity of zinc chloride becomes smaller, delta G becomes more negative. That is, as the zinc chloride becomes more stable, as its chemical potential decreases, as its activity decreases, whatever, the reaction goes to the right. If you make the zinc in this solution more stable, it drives the reaction to the left. The zinc doesn't want to leave the solution, it wants to stay in the solution. Okay, so the zinc is down here, and as you decrease the activity of zinc, you increase delta G, make it more positive, drive the thing back. So that's, I don't want to spend too long on all this, but I think it's so fundamental that we should discuss it. I already continue on here. I already talked about ideal Raoultian solutions, so I won't go through all that again. Then we talk about excess properties. So this is just definitions now. So in reality, gold and copper are not identical, and so gold-copper solutions are not perfectly ideal. And the difference between a solution property and its value in an ideal solution is called the excess property. Okay, so the excess Gibbs energy is the Gibbs energy of the solution minus the Gibbs energy of the ideal solution. Okay, the excess enthalpy is the difference between the real enthalpy and the ideal enthalpy. Okay, so excess property depends upon how you define ideality. Okay, it's the deviation from ideality. If we say for the moment we're saying an ideal solution is Raoultian, one in which the activity is the mole fraction. That's not the only definition. When you get to more complex solutions such as salts or slags, when you have 2 sublattices and so on, then you want to define an ideal solution differently. Okay, but for the moment, however you happen to define an ideal solution, the excess property is equal to the real property minus the excess property. Okay, now since in the ideal solution, the heat of ideal solution is the ideal mixing heat is 0, so the excess enthalpy is the same thing as the enthalpy of mixing. That's only true for the case of H, where the ideal is equal to 0. You generally then you rarely do you actually see H excess. Most people just talk about delta H because delta H is, in fact. So we say the excess Gibbs energy then is clearly the H excess. My S excess is clearly the difference between delta S ideal and delta S ideal and delta S real. G excess is H excess minus T S excess. Since H excess is delta H, you can generally write it this way. So the excess Gibbs energy is the heat minus the excess entropy. So if a solution deviates from ideality, there's two parts. It can deviate from ideality because the enthalpy is not ideal, or because the entropy is not ideal. If the enthalpy is mixing is negative, that gives you a negative contribution to GXS and makes the solution more stable. If delta H is positive, it gives you positive and makes the solution less stable. That's because of the bond energies. Similarly, the excess entropy, if the excess entropy is positive, that is, the solution then has a higher entropy than an ideal solution. That makes it more stable. It has a higher entropy, it has more disorder, it's more stable. That gives a negative contribution and makes the solution more stable by lowering G excess. If the excess entropy is negative, that is, the solution is ordered. If the solution, which is usually the case, if the solution is more ordered than an ideal solution, the entropy is not as positive as an ideal solution. The ideal solution has a positive entropy, and that's the disorder. If the solution is partially ordered, it will have a lower entropy. So for a partially ordered solution, SXS is negative, and that then gives a positive contribution to GXS, destabilizing the solution. So as the solution becomes more ordered, it's a tendency, the ordering lowers the entropy. The solution is not as stable as if it were completely disordered. And any solution, and we're talking about all the rest of the course really in the modeling, is that a solution will always try to minimize its Gibbs energy. So it will always try to get the lowest GXS possible. And it has to do this by balancing this off. It finds the best compromise. It finds the best value of delta H and SXS, which will give it the lowest GXS. So let's say, for example, you have a solution of A and B. They're all mixed randomly. Now let's say that AB bonds are stronger than AA and BB bonds. Okay, so there'll be a tendency now for A's to surround themselves with B's. So you'll have AB, AB, so this will, by A's surrounding itself with B's, you have then more AB nearest neighbors than you would in an ideal solution. So you got a lower heat. So the system becomes more stable because you got more negative enthalpy. But now the systems become more ordered, so you have a negative excess entropy, so this term here then becomes positive. So as the solution becomes ordered, it becomes ordered in order to make delta H more negative, but then the second term becomes more positive, and it has to find the amount of ordering that balances the two off. That gives you the lowest, that minimizes G excess. In general, that's what it's sort of all about. The system will try to balance off the entropy and the enthalpy effects in order to come up with the lowest Gibbs energy. But there's always two effects. There's the order. It's trying to maximize the disorder in order to get the most entropy, and it's trying to minimize the enthalpy in order to get the lowest bond energy, the strongest bonds in the solution. So those are excess integral properties. Remember, this is the integral Gibbs energy mixing, so this is the excess Gibbs energy or the excess integral Gibbs energy. This, then you can define partial properties. You can have an excess chemical potential, which is mu minus mu I, or delta mu I minus delta mu I, which is RT log activity minus RT log X. Okay, so that's your excess chemical potential, or your excess Gibbs energy. Mu excess I is the same thing as G excess I. Chemical potential is the same as a partial Gibbs energy. So the excess chemical potential is equal to delta mu I, which is RT log activity of I, minus delta mu I ideal, which is RT log Xi. The excess entropy, excess partial entropy, is the difference of the real partial entropy and the ideal partial entropy. The ideal partial entropy being R log Xi. And you can just keep putting things together like that. And just as delta G is equal to x1 delta G1 plus x2 delta G2, well, you can do the same thing with the excess properties. The excess integral Gibbs energy is the weighted sum of the excess partial Gibbs energies, where mu excess is G excess gold, mu excess gold. So G excess is x1 G excess 1 plus x2 G excess 2, or mu excess, whatever.
and the excess entropies, and the partials, and so on. And I did that little, everything that, you know, applies to the integrals applies to the partials. So I did that little, I have to write it down. When I had the tangent, I showed that one way of through the tangent, I said g excess of I, g of I, or mu of I was g plus 1 minus xi. You can do the same thing with the excess properties. So if you have if you plot u excess, if you plot g excess like this, then let's say in B, this point here is mu excess B at this point. This point here is mu excess of A at that point. And that equation clearly applies. All right, so these are just, looks like a lot of equations, but they're all virtually the same thing. In actual gold copper alloys, G excess is slightly negative, so the Gibbs energy is more negative than the ideal, and so the solution is more stable than an ideal solution, and then we say that the solutions exhibit negative deviations from ideality. If G excess is positive, then we say the solution exhibits positive deviations from ideality. Activity coefficients are defined this way, at least for when we're talking about Riolchin ideality. If we define an ideal solution as activity equals x, then that's the activity coefficient, which is just another way of looking at the deviation from ideality. Gamma I is equal to 1 in an ideal solution. And if you then went back to this equation here, where you see that excess partial Gibbs energy is RT log activity minus RT log x, okay, which is then RT log activity over x. So clearly the excess chemical potential is equal to RT log gamma. So if the activity coefficient is 1, the excess chemical potential is 0. There is no excess, it's ideal. If gamma is negative, the activity is less than the mole fraction, and the mu excess is less than 0, meaning it tends to go into solution, it's more stable. And if it's positive, if that gamma is greater than 1, then mu excess is positive, the activity is greater than the mole fraction, and so that tends to make the solution less stable. So this is just... Okay, that's a whole lot of mathematics, but and I did also have this yep.
If you have to show like the solution has a negative deviation from identity or positive, we should look for like G excess or
G excess, yeah.
The only one.
Yeah, G excess is negative, you have negative deviations from ideality.
Okay. You cannot discuss it based on
Well,
delta H.
Yeah, but it's a mixture of both. I mean, you can have delta H could be slightly positive, but if the minus TS excess term is so much as to make it negative, then it's not. You have negative deviations from ideality. Okay, it's used a little. Terminology is never used quite right. It is possible at a certain composition in a solution, for example, to have the activity coefficient of one component can be negative, and the activity of the other could be positive. You can have that in a solution. Okay, so now what do you say? You have a solution in which the chemical activity of one component is gamma is greater than 1 for one component, so you could say, okay, you got positive deviations for the one component, you got negative deviations for the other component. So then it becomes a little vague of what you're talking about. Although you could then take the total x1 log activity 1 plus x2 log activity 2 and see if that was positive or negative. That would indicate at least whether the G excess was. But yeah, you can. But it's always chemical potential, which is partial. It's either the partial Gibbs energy or the integral, either the partial excess Gibbs energy mu excess I or G excess. It's not H and S independently for sure. Well, okay, somebody might say I have positive deviations in H and negative deviations in S, but I mean, if you said the solution shows negative deviations, you really mean G. But yeah, people will use it kind of vaguely. Just because delta G, just because the integral is negative doesn't necessarily mean both partials will be negative. You can actually have
the solution in which.
Balance.
Yeah, if you have. That's not good. So let's say I have the solution here and I'm plotting GXS. And this would be 0 here. Say we have a, say GXS looks something like that. So GXS is always negative. But if I take a tangent at this point here, this is GXS of A, which is negative, but we could end up with a positive GXS of B. So in other words, gamma B then would be greater than 1, gamma A will be less than 1, or mu XS of B is greater than 0. Mu XS of A is less than 0, but GXS, which is XA mu XS of A plus XB mu XS of B, is in this particular example.
And so that's all the equations I can think of for the okay, this was at the end of this slide here. I did have a slide 2 which summarizes the whole thing up kind of again. That's just what I just said. There's another summary of it if you'd like to see it all summarized. All the equations that you can sort of come up with. All right, so I'll stop there. Take a break, but after the break I will go to these ideal solutions slide again. This was the ideal solution PowerPoints. And we go down the ways here. We'll talk about regular solutions.